building software for science. Libraries are really important because they enable us to scale, because first, abstractions reduce cognitive load, that's crucial, and second, they enable code reuse. So I can use some algorithm that you wrote and that I'm not clever enough to understand, and that's crucial. So examples of libraries I've been involved in, Scikit-learn. Our goal is to make research in machine learning usable to people who do not understand models and algorithms. That's our goal. I think we're partly successful. And another library I've been involved in, which is a smaller library, is NiLearn, where our goal is to make it easy to understand, to answer neuroimaging problems, so brain imaging problems with machine learning. So the challenge that Scikit-learn faces is that the space of machine learning model is huge, and it's hugely diverse. Another challenge is that the coding concepts are the easy one. The statistical and machine learning concepts are the hard one. And in NiLearn, we face a very specific challenge. That's a very interesting one, is that my goal is to onboard technology-adverse users. And it's a strong goal for me because I think if I want to have an impact on brain science, we need to achieve that goal. That's very important. So we need to design tools that reduce cognitive overhead. This is really a design problem, right? And when I mean design, I mean industrial design. I mean designing cars, designing bikes, designing forks. So there's this field of expertise that's called industrial design, and it's people that basically sit down and worry about how everyday tools are going to look like. And so did you realize that the number 4 person at Apple, Jonathan Ive, is an industrial design person? It's a person who was designing microwaves before he went to Apple, or chairs. So Apple has quite clearly understood the importance of industrial design, and you feel it when you use their product. So I think actually SciPy, the SciPy community, has understood that quite well. So I'd like to say, SciPy code different. Design is a hard problem. It's a very hard problem. So I'd like to propose a few design principles for the SciPy stack. And this is me trying to play the Zen of Python thing, so it's bound to fail, basically. But I'm going to give it a try anyhow. So the first thing I learned, and I actually learned this with Prabhu, is consistency. Consistency. So I remember a pull request where I had written a 2-word argument with no underscore between the 2 words. And Prabhu was like, this is inconsistent with our coding guidelines. I was like, this guy is so much attention to detail. But it really matters. So if you look at, this is not to bash libraries, right? When I come up with problems, it's not to bash libraries. I can't come up with these problems in Scikit-learn because we've fought them and we've removed them all. But if you look at SciPy, for instance, some of the SciPy optimized functions take max iter with no underscore, and some of them takes max iter with 1 underscore. I need basically to store this in my memory or to look it up each time. And I've got a tiny memory, so it doesn't work. So that's an example of cognitive overload. Something that's very important to me is that functions are easier to understand than classes. Objects have hidden states. In some situations, it's extremely useful. If you're doing a graphical user interface toolkit, you have hidden state by construction. But that hidden state is something that the user needs to have in mind. The other thing is that objects do not have universal interface. They have no clear entry point and no clear output. So functions are actually much more reusable than objects. And if I say this to a software engineering person, that software engineering person will immediately tell me that I don't know how to do object-oriented programming because anybody who knows how to do object-oriented programming properly knows that objects are more reusable than functions. So I claim I do know because I've worked with Prabhu Ramachandran, so I do know how to do object-oriented programming. And the problem is if you're trying to go across library bounds, objects traverse very poorly library bounds because objects come in with their own set of conventions and concepts. So relatedly, a library should hinge only on a small number of concepts. And what I mean by this is if you've understood how to use one end of the library, can you transfer this understanding to another end of the library? Now, this is a hard design problem. I don't think it's something that if I were to start a new library, I can get right the first time. I need to iterate on this. The question is, I need to find out what are the domain concepts, the handful of domain concepts that are useful, that are universal, and that I need to hang on to and to move around. I like to stress that common data containers make the ecosystem stronger. So if you have a function that takes as an input an object that's a Earth factory model, and you're trying to use this thing, you have no idea what an Earth factory model is. And maybe it's nothing more than what could be shown as a dictionary of mapping of the Earth, data mapping the Earth. And if it was written, this is a dictionary which has this and this inputs, this and this keys, or I don't know, Panda data frame or something. But basically, if a library defines its own data containers, there's a big cost to switching to this library. So each function should have one and only one purpose. The most dangerous thing is when there's a change of behavior depending on the input type. And for me, the most obvious example is git checkout. Depending on whether what goes after git checkout is the name of a branch or the name of a file, it behaves extremely different, which creates a very surprising behavior. So it's very important to code for interfaces. What I mean by this is you're coding expecting objects to expose a set of attributes and methods, and this defines their interface, and this is how you move objects around and you use objects around your library or other libraries. That said, it's also important not to overdo duck typing. And a good example is the NumPy matrix. If you code a function expecting that you're going to get arrays, and that function multiply arrays, and somebody shoves in this function in matrix, it might very well work for a certain definition of work. Basically, you'll get wrong answers. So that's a good example, I think, of having gone too far with the idea that you have an interface, but different behavior behind this. I think that properties are there for impedance matching and not for anything else. I don't really like properties because they obfuscate the data model of the objects, and I think that understanding the data model of the object is something important. And they can also create hidden compute costs. So basically, if a property has a large computation. So I think that properties are things that should be used to fix interface bugs, but they shouldn't be used to build an API. There are notable exceptions to this. I mean, the ND array shape or ND array number of dimensions are good examples of useful use of properties. But as a library designer, I worry about using too much property. Shallow is better than deep. I personally understand an object by using it. I don't understand an object, well, sometimes by reading the code. But if when I use the object, I tab complete and there's 163 methods on it. I have no idea what this object is. If I need to go in sub-objects, maybe twice down the line to understand how to modify something about my end user problem, it's very hard for me. So composition, anybody who does object-oriented programming will tell you that composition is a good thing. The problem with composition is it creates a large cognitive overload. Error messages matter. They matter hugely, and it's actually possible when you're building a library to do good error messages. So a good error message explains the problem. A good error message prints the offending value, and the reason you need to do this is because maybe you didn't put this offending value. Maybe this offending value was read from a file or something like this, so you don't understand why it's wrong. Or maybe there's something in the offending value, maybe there's a UTF-8 character hiding in it. The other thing that we've learned, and many others have learned, is that catching errors early is important, which is hard and which actually has a tension with the idea of duck typing, because catching errors early means that you're going to start, type checking basically what comes in. And if you type check too aggressively, you're reducing the kind of data that your user can put in. But if you don't type check aggressively enough, the thing is going to break after an hour of computing and deep down the stack. It's a hard but important problem. And finally, be Pythonic. And what I mean by this is avoid syntax hacks. It's possible to do crazy things with Python, whether it's overloading operators, whether it's looking at the stack and changing your behavior depending on the stack. Those things are possible. Don't do them. The reason they're extremely useful, the reason it's extremely useful to have crazy things possible in Python is to have things like profilers or debuggers or basically tools that inspect the runtime to help you understand it. But I don't like to integrate this in the design of a library because it makes the library surprising and hard to understand. So I made a scikit-learn cheat sheet because there were, other cheat sheets at the conference. And here it goes. To create an estimator, you create an estimator. To fit the estimator, you call the fit method. To predict with the estimator, you call predict. And to transform data, you call transform. Okay, I'm a bit tongue-in-cheek here, right? I just wanted to display that with scikit-learn, we thought, actually we went through a few iterations on how to make the API as clear as possible, and it won't be fully clear. Some people would like fit to be called train. Some people would like predict to be called test. Depends on the culture. So there's a strong cultural aspect to APIs. The estimator is a contract, and this is only part of the contract. It's slightly more elaborate. Because we have this strong notion of an estimator that comes with a contract, it has created an ecosystem of packages that live around scikit-learn. And some people have said that maybe scikit-learn's biggest contribution was fostering this ecosystem, because this ecosystem does much more than what we can do. This ecosystem, importantly, is based on duck typing and not inheritance. The idea being that you don't have to depend on scikit-learn to be usable with scikit-learn. And that's a great thing of Python. Now let's look at NumPy. NumPy is, to me, the basis, the foundation of our ecosystem. What NumPy really is, for me, the ND array, it's really an abstraction over pointers and operations. And it has one contract, which is the memory layout. So in my opinion, maybe NumPy has gone a bit too far in terms of number of methods, though this is debatable. The thing is, it added after the array protocol, which makes it really easy to create an object that's usable as a NumPy array in most situations. So the array protocol makes it easy to quack like an array. And I'd like here to plug one thing. There are a bunch of developers in the room. If you're interested in data in Python, I think that the ecosystem strongly needs categorical D-types in NumPy, because basically NumPy is our universal way of describing data, and we can't describe the fact that data is categorical in this universal language. So we need to use other ways of doing it, and that's not universal. In terms of designing libraries, I think of it as example-driven development. So we build our libraries based on examples, and I'd like to say that the three-liner should be the new cool, because it's great to teach others, but it's also great to teach yourself things. So the way we work is that we write examples that solve end users' problem, and then we iterate on those API until we find those examples simple and pretty. And this can take years. With Nylearn, it's an ongoing process that's been ongoing for years. And the reason is I want to give these examples to psychologists, and I want the psychologists to tell me that they understand them. So I'll ask the psychologist at the end if he does. So if you look at the user flow on the scikit-learn website, people land in a given page, and then the second page they hop to is the example page. The first one is the API documentation. And on the Nylearn webpage, it's actually the first page they hop to. So quite clearly, people are following this. To expose those examples, we use a tool that's called Sphinx Gallery, and the idea is that Sphinx Gallery compiles scripts in an example gallery. And so this is an example of an output of Sphinx Gallery. So we try to make it look pretty. We welcome pull requests to make it look prettier. One thing it does is the scripts are written as Python files, but they have embedded block of restructured text. And so it formats these embedded blocks of restructured text. It captures the output of the computation. It creates Jupyter notebooks out of this, and the extra little thing it does is it will, in the code examples, it will link the functions to their corresponding document page. So basically, you can hover on the code and click on a function and get its description. And the neat thing is it also creates mini galleries that can then be inserted in the function's documentation to link back to the example. So if you land on the function's documentation, you can hop to the example and vice versa. So building great documentation is crucial. It's hard. The first reason it's hard is that you need to focus on explaining the concepts and not the code. And so that's the problem of writing plain English. It's not a problem of writing code. The second reason it's hard is that in communication, less is more. The more you say, the more the information is diluted, the harder it is to find it. Relatedly, all code examples need to be extremely, extremely short. You might have, a longer tutorial that you link to. Users do not land where you would like them to land. They Google, they land in the wrong place. So you need gazillion of links everywhere. One way to improve documentations is to teach with them. I teach with my documentations, which make me hate them. So it's hard to maintain docs, but it's extremely useful. We use continuous integrations on our doc. We check all the links. We run the examples. We run the doc tests. Having done all this, I'd like to claim that Scikit-learn is the new machine learning textbook. And I think we're seeing this. People learn machine learning with Scikit-learn. And one day I'd like NiLearn to be the new neuroimaging review article. Currently, at each commit, the continuous integration runs our docs, runs our examples, and reproduce historical examples. So you can run brain reading by following this link that you're not seeing, but the slides will be online, and just run brain reading at home. This is very intensive for the continuous integration, so I should thank Circle CI, who's been hosting us and been giving us a lot of power. We've had to fight with data. If you want to make good open science, the first thing you need to do is make it possible for everybody to run that science. And we've had to fight so much to get good data available. Getting data available is easy, but because you want to demo things that are cool scientific results, you need good data. The other thing that we have to fight for is compute time. I'm a computer scientist. I design algorithm, which means that I always design the fanciest algorithm that always takes longer. So I need to fight with myself to design better algorithms that are faster and quite often simpler. This is actually great because it has forced us to distill the literature, whether it's in terms of scientific results or in terms of algorithms. Basically prioritize and focus on the important things. So this is just like writing a scientific review. That's awesome. So I'd like to claim that package development consolidates science and maybe moves it outside of the lab.